With this chapter, we're going to start looking at sources of magnetic fields. Quite by accident, it was discovered that electrical currents fill the space around them with magnetic fields. When an electric current was turned on in a wire, it was noticed that it deflected a compass needle that was sitting near the wire. So in this situation on the left, I have a wire perpendicular to the page, but not carrying any current. The current is turned off. I have 6 compasses stationed around my wire, and where are they pointing? They're pointing towards the North Pole of the Earth. They're aligning themselves with the Earth's magnetic field. Now, when we turn on a current in that wire, we get this situation. The current coming out of the page in the wire creates a magnetic field that causes the compass needles to align with the magnetic field. The magnetic field forms a circle around the wire. In this case, the magnetic field points in the counterclockwise direction. Which brings us to another right-hand rule in physics. To find the direction of the magnetic field that encircles a wire, we put our thumb in the direction of the current. Make sure it's the thumb on your right hand. Your right thumb in the direction of the current, and the fingers on your right hand roll around the wire in the direction of the magnetic field. So in this case here, my wire is coming out of the page and the current is coming out of the page. I put my thumb in the direction of the current along the wire. I know already that the magnetic field has to form a circle around the wire. I just don't know whether it's clockwise or counterclockwise. Which direction is the magnetic field point? Well, my right thumb in the direction of the current, my fingers roll around the wire in the direction of the magnetic field, and so I can see when I have a current coming out of the page, my magnetic field goes around the wire in the counterclockwise orientation when viewed from this angle. Now let's see what happens if we have a loop of wire like this one. I'm going to draw it edge on view like this on my paper. So if it has a current flowing in it, if the current is flowing in this direction, if I rotate it like this and the current is flowing this way, then the part of the wire right here where my finger is, the current is coming toward the camera. And it comes across the front, and the part over here is going away from the camera. So on my paper here, I can draw a current coming toward the camera on one side and away from the camera on the other side, or toward the observer coming out of the page on the left, away from the observer into the page on the right. So we're looking at a side view. On my paper here, I've got a side view, edge-on view of a loop of wire, and I'm drawing the current direction as you see it just at the edges. I'm not really concerned with what's happening at the front and the back, just the edges. The current forms a magnetic field that encircles the wire. So there's going to be a magnetic field that forms a circle here. And there's going to be a magnetic field that forms a circle here. And as we move away from the wire, that magnetic field will get weaker and weaker, we would expect. So the magnetic field lines should look something like this. We just don't know what direction they point. We'll use our right hand rule. Put our thumb in the direction of the current. So on this side, on the left hand side, I'm going to put my thumb in the direction of the current, and my fingers roll around the wire in the counterclockwise direction. So I'm expecting these magnetic fields to point like that. Now if we look at the right-hand side, I have to put my thumb into the page. My fingers curl around the wire in the clockwise direction. So my magnetic field points this way. So if I had a loop of wire like this, with a current flowing in it, I would expect to have the space around it filled with a magnetic field that resembles what I've drawn on the paper. Now, what does that look like? If you remember, our permanent magnets have a magnetic field that looks very similar to this. So our loop of wire with a current flowing in it acts a lot like a permanent magnet. What do we call that? An electromagnet. We can turn a current on and make a magnet. The nice thing about it is you can turn the current off and the magnetism goes away, which comes in handy sometimes. This is another image of a long, straight, current-carrying wire perpendicular to the page. And I've drawn the magnetic field lines. And what I'm trying to illustrate here is that the magnetic field drops off as 1 over r as you move away from the wire. The magnetic field gets weaker as you move away from the current-carrying wire. And I know what you're thinking. You're thinking, how do we calculate the magnetic field that surrounds a current-carrying wire? Well, we use the Biot-Savart Law. I've written it out here. Mu naught is a constant very similar to epsilon naught. Epsilon naught is the permittivity of free space, and that shows up in all of our electrostatics equations. Mu naught is the permeability of free space. That shows up in our magnetic equations. So we have mu naught I over 4 pi times the integral of ds cross r hat over r squared. It looks a little intimidating at first, this equation, but it's not so bad. We'll learn to break it down and solve this for all kinds of current-carrying wire situations. The first thing I want to mention is that mu naught is equal to 4 pi times 10 to the negative 7th Tesla meters per amp. And some textbooks don't write the Biot-Savart law like this. I like to write it this way because we used a textbook for a long time that writes it this way. The ds cross r hat over r squared is exactly the same as writing ds cross r vector over r cubed. These are identical because r vector over r is equal to r hat, a unit vector that points in that direction. So on the left-hand side, I have a unit vector in my numerator and r squared in my denominator. And on the right-hand side, I have a full vector with the magnitude associated with it. And so I have r cubed in the denominator, but these two expressions are exactly the same. The best way to see how to use Biot-Savart law is just to dive in and do an example. And we're going to do an infinite current carrying wire, a straight, infinitely long current carrying wire. So I've shown it here with the dark black line. That's my wire. It's carrying a current I to the right. And we want to know what is the magnetic field at distance r away from the wire. So our equation is this. And the first thing we need to realize is that the magnetic field is a vector property, so it has a direction associated with it. And this equation has a cross product in it which yields a direction. So we can get the direction from the cross product in the equation. That works perfectly well. Or we can think about our right-hand rule that we just learned for the direction of the magnetic field that encircles a wire. We know that this wire is going to have magnetic field lines that form circles around it. So if we're standing a distance r away from the wire in the plane of the page, that magnetic field has to be perpendicular to the plane of the page. It forms a circle around the current carrying wire. The question is, does it point up out of the page or down into the page? So I put my thumb in the direction of the current, and it tells me that any place above the wire, any place up here, my fingers are going to roll and point up out of the page. So the magnetic field, due to this wire, has to point out of the page, anywhere above the wire in the plane of the page. And if I let my fingers roll around to the other side, so any place down here, my fingers are going to roll around and point into the page. So down here, the magnetic field has to point into the page. Any place below the wire in the plane of the page. Another example is, let's rotate this 90 degrees so the wire is running toward the camera. If the current is flowing toward the camera, we know the magnetic field has to form circles around the wire, kind of like this, right? Forms a circle around it. The question is, what direction is this magnetic field? Is it clockwise or counterclockwise? Well, if the current is flowing toward the camera, I put my thumb along the wire in the direction of the current, and my fingers are going to roll this direction, counterclockwise from the camera's view. That means if I'm standing over here, the magnetic field points down. And if I'm standing on this side, the magnetic field points up. The magnetic field points tangent to the magnetic field line. If I'm standing up here and measuring the magnetic field, it points in this direction. And down here, it points in that direction. Okay, let's break this equation down and go through each variable. Mu naught is our constant, 4 pi times 10 to the minus 7. I is our current. We would be given that value in this problem. We're going to pick some little length of the current path. And that's our ds. And it points in the direction of the current. So ds, in our case here, is just dx because we're along the x-axis. It's some little tiny amount of the line that makes up the current path. And it points in the direction of the current. R hat is a unit vector that points from ds to our point of interest. And our point of interest is over here. So R hat points in that direction. And this big vector that is R. R is the vector that connects ds to our point of interest. So ds cross R hat, let's see, what is that? Well, when we do a cross product, we take the magnitude of the first vector, the magnitude of the second vector, and the sine of the angle we get when we put their tails together. That means we're interested in this angle right here. And the direction is given by the right-hand rule. So ds points in the x direction, and r points sort of up and to the right. So when I do the cross product, I get a vector that points out of the page. Or in this case, if I use my x, y, z coordinate system, it points in the z direction. So that's the z hat or k hat direction if you like I, j, k instead of x, y, z for your unit vectors. Well, what is ds? I told you I was going to just use dx for that because it's along the x-axis. R hat is a unit vector, so it has a magnitude of 1, and the sine of theta we'll get to in just a second. Let's go back and look at our image. What is the sine of this angle? The sine of this angle is the opposite side, that's r, divided by the hypotenuse, which is lowercase r. So I'm calling the distance away from the wire capital R, opposite over the hypotenuse. And lowercase r is a variable. It changes because ds is going to be a little segment and we're going to integrate over the whole wire. So r is a variable. R is going to change because ds starts way out here at infinity and it comes all the way in and goes all the way out to infinity on the other side. So that's a variable that changes. But this capital R is not a variable. That's a fixed value. That's where we want to know what our magnetic field strength is at that location, or point of interest. So there's only one more thing I need to define here, and that's R. This is a right triangle. So that means that I can use Pythagorean theorem. And this side is x. This side is just x. My ds is located at any point x. And I'm going to integrate that from negative infinity to positive infinity. So this is just x squared plus r squared square root. I'm hoping that you're seeing some similarities here to the integrals we set up to find the electric field from a charge distribution. We did very similar things there. We had sine and cosine thetas, and we used a right triangle to find out what sine and cosine theta were. And we integrated over the charge distribution. Well, we're doing very similar things here. We're using a current path. We're going to integrate over the current path, and we're going to find the magnetic field that it produces. So let's start plugging some things in. We've got our magnetic field, mu naught I over 4 pi, the integral of dx sine theta over r squared. And we said sine theta was just r over lowercase r. So that gives us an r cubed in the denominator. And we know what r is in terms of x. Remember, just like with electric fields, once you know what you're integrating with respect to, you want to convert all your variables into that one so you can integrate with respect to it. So once we know that we've got a dx in there, we want to turn everything else. We want to turn our r into an x. And so how do we do that? Well, we're going to use this substitution. So we have x squared plus r squared to the 3/2 power because we have r cubed and r is the square root of x squared plus r squared. And what are the limits of integration? We want to integrate over the entire current path. And this is an infinitely long straight wire. So we will integrate from minus infinity to plus infinity. And we can make this 2 times the integral from 0 to infinity. R is a constant, it comes out, and I get x over this is just 1. So I get the magnetic field is equal to mu naught I over 2 pi r. This is a vector quantity, so I could have a z hat, because in this case it came out of the page, remember, in the z direction. So in general, I'll take off the vector sign from my magnetic field because this is the magnitude of the magnetic field, and I'll use a lowercase r because it could be any distance away from the wire. The magnetic field, a distance r from an infinite straight current carrying wire.